So, hello and welcome to week 5 of the NPTEL Algebra-II course. So, I am one of the TAs for this course. My name is Shubhajit Das, and I hope that you are also attending the other TAs course. The other TAs sessions. So, yeah, so as we keep doing every week, we'll be solving problems from the weekly assignments. And so, without much ado, let us start. Okay, so let us have a look at the first question. So it says that suppose K is any field and consider or suppose that S3 is a subgroup of the automorphism group of K. Then we need to find out what is the degree of K over K power S3. What is K power S3? As you can recall, it's just the fixed field of S3 in K. Okay, so what is it precisely? K power S3, if you recall, the fixed field of S3 in K is rather the subfield of all elements alpha in K which are fixed by every element of this G, right? Every element of this subgroup. So sigma of alpha is alpha for all sigma in S3, right? Okay, so yeah, I have slightly abused the notation. Actually sigma of alpha only makes sense provided that for sigma in S3 makes sense provided that S3 is strictly a subgroup of odd K, but it could happen that S3 is a subgroup of odd K up to an automorphism. Okay, so I'm referring to that particular automorphism corresponding to sigma in S3. I'm looking at its image in odd K and I'm applying that automorphism on alpha. And if sigma of alpha is alpha for all sigma in S3, or rather for all images of all elements of S3, then we say this particular I'll include alpha in the fixed field. Okay, anyways, so this one is very easy. So if you recall, if G is a finite group of automorphisms of a field E, then the degree of E over E power G is exactly equal to the cardinality of G. Okay, and you prove it in by showing that both, so you have inequalities in both directions. That is, first of all you show that E is to E power G is less than or equal to cardinality of G, and then you show independently that E is to E power G is greater than or equal to cardinality of G, and then you have this. So this is a popular theorem that I hope you have learned previously, and using this we therefore have that K is to K power S3, this degree is exactly equal to the cardinality of S3, which is 6, and there you have it. It's very simple. So the answer will be 6. Okay, so let us move on to the next problem. Okay, so now again K is taken to be an arbitrary field and we consider D4 as a subgroup of the automorphism group of K. Okay, so now D4 is a dihedral group, as you know, and you again consider the fixed field of D4 in K, which is taken to be F. Okay, then we have these 4 questions, which of them are correct. So K over F is clearly an extension because F is a subfield of K. So K over F is a separable extension. This is the first one, which means that it's an algebraic extension such that every element of K is separable over F. That is, for any element of K, the minimal polynomial of that element over the base field F is a separable polynomial. Option B says K over F is a normal extension, which means that, as you know, it's an algebraic extension and every irreducible polynomial over the base field F that has a root in K will split completely over K into a product of linear factors. Okay, that is, every irreducible polynomial over F that has a root in K will actually have all its roots in K. And we also know that if it's equivalently if it is assumed to be finite and normal, then it is, then an equivalent definition of a finite normal extension is that it's a splitting field of some polynomial over the base field. Splitting fields are normal by definition. Then C says K over F is a Galois extension, and as you know, there are various equivalent ways of defining Galois extensions. Either you for finite extensions, either you define the extension to be finite, normal and separable, or you define the extension K over F to be the splitting field of some separable polynomial over the base field. Or you can define it like this, that the fixed field of the Galois group of the extension, so first of all it should be a finite extension, and the fixed field of the Galois group of the extension in K should be equal to the base field F. Or you can also define it like this, that the degree of the extension is precisely equal to the cardinality of the Galois group of K over F. Okay, all these are equivalent ways of defining Galois extensions. Another equivalent way is this, that F should be equal to the fixed field of G in K, where G is some finite group of automorphisms of K. Okay, so any of these equivalent statements will work. So anyways, so we need to figure this out. We need to work with the extension K over K power D4. Now we know that K over K power D4, the degree of this extension is exactly equal to the cardinality of the group D4, right? This is what we know, which implies, so this is exactly equal to the cardinality of D4. Now check, this is very simple, that D4 is always a subgroup of the automorphism group of K over F, I mean K over K power D4. If you look at the automorphism group of K over K power D4, then D4 is clearly contained in this. It's a subgroup of this, right? This you can easily check. And now what we do is, we therefore have this. Thus, what we can say is thus D4 okay, so what we want to show is that D4 is exactly equal to the Galois group, right? This is what we want to show, right? So okay, thus we have that cardinality of D4 is less than equal to the cardinality of automorphism group of K over K power D4, right? And what is the, and we can say that the cardinality of K over K power D4, the automorphism group of K over K power D4 is less than equal to K is to, that is the degree of this extension, which is exactly equal to D4. Now why is this later inequality, I mean why do we have this later inequality? This follows from this very easy theorem. I hope you have done this in, I guess you can find it in Dummit-Foot as well, that if E over F, okay, so assume that let Fx belong to some field Fx, okay, be a polynomial. We don't, yeah, I mean let Fx in capital Fx be a polynomial, and let E over F be an extension which is generated by the roots of Fx in E. So what it means is, if you take Fx in capital Fx, and if you assume that E over F is some extension such that if alpha 1, alpha 2 dot up to alpha m, let's say, if this I mean this particular set is precisely the set of roots of Fx which are contained in the extension E, then E must be equal to F adjoined with these roots, okay? So if E over F be an extension generated by the roots of Fx in E, and if omega over F be an extension, be any extension of capital F over which the polynomial fx splits, then the number of f homomorphisms, that is field homomorphisms which fix f element wise, number of f homomorphisms from E into omega, the number of such mappings of E into omega which fix f element wise, the number of such f homomorphisms of E into omega is at most the degree E is to f. Okay, and it is precisely equal to E is to f if the polynomial fx has distinct roots in omega. Okay, that is in other words, if the polynomial fx is a separable polynomial, that is fx has only simple roots, it has no multiple roots. So since omega is an extension over which fx splits, that is fx has all its roots, so if fx has distinct roots in omega, then the number of such f homomorphisms from E into omega will be exactly equal to E is to f. But we of course don't need this part for solving this problem. We just need the fact that the number of f homomorphisms from E into omega will be at most E is to f. Okay. So using this fact, we therefore have this inequality. Okay, that the cardinality of the automorphism group of k over k power d4 is less than or equal to the degree of the extension. Why? Precisely because an automorphism of k over k power d4 is just a k power d4 homomorphism, that is it's a homomorphism from k to k, it's an isomorphism from k to k which fixes k power d4, right? Now k over k power d4 is a finite extension, as we clearly saw, and therefore you do have that it's generated by finitely many elements which are algebraic over k power d4. So using these elements you can cook up a polynomial fx, okay, such that k is exactly equal to the the extension k over k power d4 is generated by the roots of fx in k, and you can take some splitting field omega of fx. Okay, now you can apply this particular theorem. So the number of k homomorphisms, k power d4 homomorphisms, that is homomorphisms which field homomorphisms which preserve k power d4 or which fix k power d4 element wise, number of such homomorphisms from k to omega will be at most equal to the degree of the extension, right? And the number of automorphisms of k over k power d4 will be less than or equal to the number of homomorphisms from k into k power d4. The number of such homomorphisms from k into omega, right? And this will be less than or equal to the degree of the extension. Okay. So I hope I am not I hope I sort of said the argument correctly. So anyways, so this is a popular inequality. I do hope that you are well aware, even if you didn't understand what I said just now. But if you have any questions, you can write to me. So yeah. So yeah. So what we have, the upshot is that on the left hand side of the inequality we have cardinality of d4, and on the right hand side we also have cardinality of d4, which means all these inequalities are equalities, and therefore what we have from here is that the cardinality of the automorphism group or the Galois group of k over k power d4 is exactly equal to the degree of the extension k is to k power d4, right, which implies that k over k power d4 is a Galois extension. Okay, this is one of the defining properties of a Galois extension, that is the cardinality of the Galois group of the extension should be equal to the degree of the extension. Okay, one of the defining properties of a finite Galois extension, that is the cardinality of the Galois group of the extension should be equal to the degree of the extension, and therefore we certainly have option A is correct, option B is correct, option C is also correct, and finally automorphism group of k over k power d4 is equal to d4 as well, as d4 is contained in this, as we saw or I asked you to check above, and they have the same cardinality. since these two have the same cardinality, hence they have to be equal. They are finite, they have the same cardinality. One is contained in the other, so they have to be equal. So option D is also correct. So all options are correct. Okay, let's move on to the next question. Okay, so let F1 and F2 be Q automorphisms of Q root 2 comma root 3, which means that F1 and F2 are elements. They are elements of the Galois group of Q root 2 root 3 over Q. And it is said that F1 and F2 both map root 2 onto the same element, and F1 and F2 again map root 3 onto the same element of Q root 2 comma root 3. That is, their images in Q root 2 comma root 3 are the same under both these maps. So we need to figure out which of these are correct. Option A, option B and option C. Okay. So option A is clearly correct. As see the fact that F1 so okay, so yeah, as how should I explain this? Okay, as F1, okay, so let me correct. Why? You take this automorphism F1 F2 inverse, which is an automorphism of Q root 2 comma root 3 into, and hence since it's an automorphism, onto this, onto itself. So now F1 F2 inverse fixes Q element wise by definition, as F1 and F2 do so. F1 F2 inverse fixes root 2. Why? Precisely because F1 and F2, as given by the first equality, F1 and F2, which are mappings of Q root 2 comma root 3 into itself, F1 and F2 both map root 2 onto the same element. So F1 maps root 2 onto the same element as onto which F2 maps root 2, and F1 and F2 again map root 3 onto the same element. So the image of root 3 under F1 and F2 is the same, right? So F1 of root 3 is some element of Q root 2 root 3, and F2 of root 3 is again some element of Q root 2 root 3, and these two elements have to be equal, which is why I am saying that F1 and F2 both map the element root 3 onto the same element, and thus F1 F2 inverse fixes root 2 and root 3, which implies that F1 F2 inverse must also fix the extension Q root 2 comma root 3 element wise, and which therefore implies that F1 F2 inverse is equal to identity, which implies that F1 must indeed be equal to F2. Okay. So option A is certainly correct, which shows that option B is incorrect. Now what about option C? Is it can it be possible that both F1 and F2 are the identity maps? Okay. So we can just give an example to show that this won't be true. So we can just give an example of F1 which is not identity. So take the automorphism, take the mapping of Q root 2 comma root 3 into itself. So we take, if we define this automorphism to be F1, it's a mapping of Q root 2 comma root 3 into itself, and we define it like this, that it fixes Q. So it fixes Q, it maps root 2 onto root, let's say it maps root 2 onto minus root 2, and let's say it maps root 3 onto root 3. Okay. and it fixes Q. So that you have the automorphism on the entire domain. So you need to check this. This is, you need to check. You can't just decide some images of some generating elements and then say that this defines an automorphism on the entire field. You need to check that this is indeed an automorphism. Okay, so you have well definedness and all those things, and this will be true precisely because root 2 and root 3 are that is a very crude way of saying what I'm trying to say, but yeah, please try to check that F1 is indeed an automorphism, that is indeed a well defined automorphism. Indeed an automorphism of Q root 2 comma root 3. And I'll just summarize the argument. So not summarize, rather give an hint for the argument. So the idea is to see that Q root 2 comma root 3 considered as an extension of Q is a Galois extension precisely because it is a splitting field of the separable polynomial x square minus 2 times x square minus 3 over Q, right? And it's a Galois extension, and you can check that the degree of this extension is precisely 2 times 2, which is 4, which means that the coordinate of the Galois group of this extension is 4. Now if you take any automorphism sigma of Q root 2 comma root 3 fixing Q, that is if you take any element sigma in the Galois group of this extension, then since sigma fixes Q, sigma must fix roots of, since sigma fixes Q, sigma should permute roots of polynomials over Q, right? So in particular, sigma permutes roots of x square minus 2, which is a polynomial over Q. So the only possible images of root 2 under sigma can be either minus root 2 or root 2 itself. And the only possible images of root 3 can be either root 3 or minus root 3, because sigma fixes, sigma permutes roots of x square minus 3 as well, which therefore shows that the number of possibilities, the number of such elements sigma, the number of elements in the Galois group of Q root 2 comma root 3 over Q can be at most 4, right? Because for root 2 you have 2 images, for root 3 you have 2 images, and Q is already fixed. So this means there can be at most 4 elements, and since we computed that the degree of the Galois group, which is equal to the degree of the extension, is 4, so all these 4 elements are exactly automorphisms Q root 2 comma root 3. What this says right now is that in particular the map root 2 going to minus root 2 and root 3 going to root 3, for example, let's say, is actually an automorphism in the Galois group. It's actually an element in the Galois group. So hint, check the video maybe. Okay, so if you have any questions you can ask me, otherwise I'll move on to the next problem. Yeah, so this need not be true because we already gave an example of a map F1 which you can also take the it's not complete, and take F2 to be a mapping of Q root 2 comma root 3 into Q root 2 comma root 3, which sends root 2, we can just take the same map, root 2 and root 3 onto root 3. Yeah, they have to be the same map as we proved in part 1. So take F1 equal to F2 to be this particular mapping, and you see that this is clearly not identity because F1, which is equal to F2, actually doesn't fix root 2. It maps root 2 onto minus root 2. Okay, yeah, if you have any questions you can ask me, otherwise we'll move to the next problem. So do you have any questions? Ranjitham. I'm audible, right? Can someone unmute and let me know if I'm audible or not? Excuse me. Am I audible? Maybe someone can write it down in the chat if I am audible, because I am unable to understand otherwise. Thangeshwaran, am I audible? Can you just let me know if I am audible? Okay, so I hope there are no issues there, but if you have, please feel free to unmute and speak. So anyways, let's move on to problem 4. So we are taking M to be Q adjoint with I, M prime to be Q adjoint with omega, where omega is e to the power 2 pi I by 3, which is a primitive cube root of unity, and we take M double prime to be Q adjoint with both I and omega. Then we need to figure out which of these particular options are correct. So option A says that automorphism group of M over Q should be isomorphic to Z2. So A is correct, as this is very trivial as before, as M over Q is the splitting field of x square plus 1 in Qx, right, which is separable. So that M over Q is Galois and cardinality of M over Q, cardinality of the Galois group of M over Q is equal to the degree of this extension, which is precisely 2, and thus the automorphism group of M over Q, or the Galois group of M over Q, is isomorphic to Z2. B is incorrect, as M prime over Q is Galois, being the splitting field over Q of the separable polynomial x square plus x plus 1 in Qx, right? It's M prime is clearly the splitting field of this. M prime is just Q adjoint with some with e to the power 2 pi I by 3, right? But cardinality of the Galois group or automorphism group of M prime over Q is exactly equal to, it's exactly equal to the degree M prime is to Q, which is 2 and not 3. So the automorphism group cannot be Z3, it has to be Z2. So option C says that the automorphism group of M double prime over Q is isomorphic to Z2 cross Z2. So yeah, so this is again true, C is true, as M double prime over Q is the splitting field of the separable polynomial x square plus 1 times x square plus x plus 1 over Q, and hence Q is Galois with Galois group of order 4, and since sigma, I mean any element of the Galois group, so maybe I'll make some space here. Any sigma in Galois group of m dot prime over Q permutes the roots of x square plus 1, which is I and minus I, and also permutes the roots of x square plus x plus 1, which is omega and minus omega, sorry, which is omega and omega square, so that every sigma in the Galois group of m double prime over Q has order 4, I mean order 2. Thus the Galois group of m double prime over Q has to be isomorphic to Z2 cross Z2. It can't be Z4. There is no element which generates the group. There is no element of order 4 in the Galois group. Every element has order 2, which means that since it's a group of order 4, there are two possibilities, either Z2 cross Z2 or Z4, but Z4 can't be the case, which means that the group is isomorphic to Z2 cross Z2. So option A is correct, certainly. Option B is incorrect, as we saw. Option C is correct, and therefore option D is incorrect. So let's move on to the next problem. Okay, so let F5 be the finite field of order 5. We need to choose all the correct options from this. Okay, so option A says that if you consider F5 power 4, which is the finite field of order 5 to the power 4, there is up to isomorphism exactly one finite field of order 5 to the power 4, right? The Galois field of order 5 to the power 4. And A has to be incorrect. Why? Because if you consider any finite field of order a power of 5, then this means that the characteristic of the field has to be 5, which means that the prime subfield of the field has to be Z5. And F5 power 4 in this case will since it's a vector space over its subfield F5, the dimension of this vector space, which is precisely defined to be the degree of this extension, right? The dimension of this vector space has to be equal to 4, right? Let's suppose the dimension is n, or the degree is n. Now you have a base field which has order 5, and if you take a n dimensional vector space over this base field, then the vector space should have coordinate 5 power n, right? So if 5 power 4 can have its dimension has to be exactly 4 as a vector space over F5, so that the degree of this extension has to be 4, as F5 power 4 over F5, how should I say it easily, as F5 power 4 has dimension 4 as a vector space over F5, right? If the dimension is n, then the number of elements in the vector space has to be 5 to the power n. Since it's 5 to the power 4, the dimension has to be 4. So this is incorrect, this is correct clearly. Option C says that automorphism group is a cyclic group. Okay, so this is again true. So general, so C is again true. True. So in general, consider any n belonging to natural numbers consider the Frobenius map, Frobenius automorphism from fp to the power n into fp to the power n, right? This is an element of the Galois group of fp to the power n over fp. Check this. This is easy, very easy. So you want to check that this so I didn't write the automorphism, sorry. Yeah, the Frobenius automorphism is defined like this: a goes to a power p. So check that every element of fp will be fixed, because precisely because every element of fp satisfies the polynomial x to the power p minus x. Okay, so it certainly fixes every element of fp. So it is an element of Galois group of fp power n over fp, and it generates the group. So you have to check this if this was not covered, and if you have any questions you can ask me, but it's very easy. Okay, so first of all, fp power n over fp is a Galois extension. That much is very easy to understand, precisely because fp power n over fp is a splitting field of the polynomial x to the power p to the power n minus x, and this is a separable polynomial over the base field, precisely because if you take its formal derivative, then the formal derivative turns out to be -1, and the GCD of the polynomial with its formal derivative is therefore equal to 1, which shows that, I mean, the polynomial and its formal derivative are relatively prime, right? Which shows that the polynomial is a separable polynomial. Okay. Yeah. Yeah, so that the extension fp power n over fp is a Galois extension, and the degree of this extension will be equal to the cardinality of the Galois group. Okay, the degree of this extension is n, so that the cardinality of the Galois group is also n. And do check that this Frobenius automorphism, which is an element of the Galois group, is actually an element of order n, so that it generates the group. Okay. So the hint, as I have said, so that I'll just write this down, that the hint is mentioned in the video. Hint, check the video. Okay, so let's move on to the next problem. Yeah, I hope I covered everyone. Yeah, so C is correct and therefore D is not correct. That is, the automorphism group is indeed a cyclic group. Let us move on to problem 6. Okay. Okay, so let K be Q adjoint with cube root of 5 comma omega, L be Q adjoint with cube root of 5, and let us suppose F is Q. Okay, now consider G to be the automorphism group of K over F and H to be the automorphism group of L over F. Okay, where omega is, of course, as you have understood, it's e to the power 2 pi I by 3, a primitive cube root of 1. Then which of the following are correct? First of all, H is a normal subgroup of G. Okay, so we know, so first of all, K over F is Galois as it is the splitting field of the separable polynomial x cube minus 5 over F. So it is a Galois extension. Now, by the fundamental theorem of Galois theory, just a minute, yeah. By the fundamental theorem of Galois theory, we know this, that if you take any intermediate subfield, let's say B, then B over F will be Galois if and only if the Galois group of K over B is a normal subgroup of the Galois group of the entire extension, that is Galois group of K over A. So L over F is Galois, that is equivalently normal here because it is already finite and separable. So this is Galois if and only if the Galois group of K over L, which is already a subgroup of the Galois group of K over F by definition of Galois groups, if this subgroup is a normal if and only if this subgroup is a normal subgroup, then we can say that L over F is Galois. Okay, so yeah, so to figure out whether so this is H and this is my G. Now to figure out whether H is a normal subgroup of G, we just need to figure out whether the extension L over F is Galois. But L over F is not Galois, right? As what is L? L is Q adjoint with cube root of 5. Okay, as x cube minus 5 is an irreducible polynomial over F, right? This is an irreducible polynomial over F that has a root in L but doesn't split, right? Doesn't have all its roots. Roots in L, right? So why am I saying this? Why does this imply that this is not Galois? Because this particular statement implies that this extension is not normal, so that it can't be Galois. So that L over F is not normal, is not a normal extension. Okay, yeah, so A is incorrect, not correct. So H cannot be a normal subgroup. Okay, so this is not correct. Certainly B is correct. H is a subgroup of G, but as we saw, it's not a normal subgroup. Yeah, so let me make some space again. So B is certainly correct. There's no doubt about this. Option C says there exists some element G in the Galois group, which so option C says there exists some element G in the Galois group that is an automorphism of G. An automorphism of the extension K over F. There exists such a G in the Galois group which maps the element cube root of 5, right, onto some element in the in L. Okay, so option C says that we can find an element G in the Galois group such that the image of cube root of 5 under G, right, which is a priori an element in K, actually belongs to L. That is G maps cube root of 5 onto some element, right? Yeah, so there exists a G in capital G such that G maps cube root of 5 onto some element in K which actually belongs to L. Okay, it maps cube root of 5 onto an element in capital K which is actually in L. Now this is option C is clearly correct. Correct, as G can be taken to be identity, right? This is clearly an element. By definition of Galois group, this is an element in the Galois group. So C is clearly correct. And what about option D? So option D says that we can find an element G prime in the Galois group as well, which maps the element cube root of 5 onto an element which is not in L. Okay, so there exists some element G prime in the Galois group G, right, which sends the element cube root of 5 onto some element in the codomain, that is onto some element in K which is not in L. Okay, that is the image of cube root of 5 or the place or the element in K onto which cube root of 5 is mapped onto, this particular element in the codomain is not in L. We can find such a G prime which maps cube root of 5 onto an element in K which is not in L. Now D is also correct. Why? I'll say why. So so K over F is a Galois extension, as we just saw, and what does any element in the Galois group do? It permutes the roots of x cube minus 5, right? Now the cardinality of the Galois group of K over F is equal to the degree of this extension. The degree of this extension, as you can check, is precisely 6, which means that there are 6 elements in the Galois group, right? And any element in the Galois group also permutes the roots of x square plus x plus 1, right? So the possible images of omega are omega or minus omega. So if we assume that every element, okay, so let me just yeah, it's better if I just write it down. Okay, so maybe let me just come up with a shorter argument to explain this. Okay, D is also correct. So any sigma in G permutes the set cube root of 5 omega cube root of 5 omega square. Okay, right? And sigma permutes omega and omega square. So the possible images of cube root of 5 under any sigma in the Galois group are cube root of 5 itself, or cube root of 5 omega, or cube root of 5 omega square, right? Oops, sorry for the interruption. Cube root of 5 omega and cube root of 5 omega square. Okay, but neither cube root of 5 omega nor cube root of 5 omega square are in L, right? Okay, so so if D is incorrect, that is, in other words, if for every element G prime in capital G, G prime of cube root of 5, which is an element in L, I mean which is an element in K, this element, if this element always belongs to L for all G prime in capital G, that is, in other words, if every element of the Galois group of the extension K over F maps cube root of 5 onto some element which is in capital L, if every element does this, that is, you take any element in the Galois group, it sends cube root of 5 onto some element of capital L. Okay, onto some element of capital L, then that is, if D is incorrect, then every sigma in the Galois group should map or maps cube root of 5 onto cube root of 5, right? It should send, sorry, cube root of 5, yeah, it should send cube root of 5 onto it, so it should fix cube root of 5, right? Because if the image is in L and the only possible images of cube root of 5 are cube root of 5, cube root of 5 omega and cube root of 5 omega square, and the later two are not in L, so the only possible image would be cube root of 5. Okay, thus the cardinality of the Galois group of the extension K over F would be, in that case, less than equal to 2, right? As there are only two possible images, right? of omega under any sigma in G, okay, and cube root of 5 is fixed by every sigma in G. So every sigma in G fixes cube root of 5 and it can map omega onto two places, right? And since any automorphism of the Galois group is completely determined by where it sends cube root of 5 and omega, so the number of automorphisms is at most 2, right? This is what would happen if we assume that D is correct, but the contradiction arises as the cardinality of the Galois group of the extension K over F is equal to the degree of the extension K is to F, right, which is equal to 6, right? The degree is 6 as we saw, so this can't happen. Okay, yeah, so let's move on to the next problem. Yeah, sorry, let me check if I have, yeah, so option C is correct and option D is also correct. Okay, yeah, maybe I'll write it down. Thus D is correct. So let us move on to the next problem now. Oops. Yeah, so we need to make spaces. Okay, so let K be equal to Q adjoint with fourth root of 2 and I, L1 be Q adjoint with fourth root of 2 and L2 be Q adjoint with I. Okay, now let G be equal to automorphism group of K over Q, right? H1 be the automorphism group of K over L1 and H2 be the automorphism group of K over L2. Okay, then we need to figure out which of these options are correct. So option A says that H2 is a normal subgroup of G. So automorphism group of K over L2 is a normal subgroup of automorphism group of K over Q. Okay, so first of all, as we keep doing, the first step that we need to see is that the given extension, the entire extension has to be a Galois extension. Okay, so check that. I will not say y again, but you can just check that it is the splitting field of some separable polynomial over Q, over the base field Q. So check that K over Q is a Galois extension. Very easy. Okay, and yeah, so now by fundamental theorem of Galois theory, H2 is a normal subgroup, so this is, yeah, okay, maybe H2 is a normal subgroup of G if and only if L2 over Q is Galois, which is correct. So this latest statement that L2 over Q is Galois is a true statement. Why? Because L2 is Q adjoint with I, right? And therefore it is a splitting field of the separable polynomial x square plus 1 over Q, and hence L2 over Q is Galois. Thus H2 is indeed a normal subgroup of G, that is A is correct. What about statement B? B is incorrect. So I claim this, that statement B is incorrect. So statement B says that H1 is a normal subgroup of G. What is H1? It is the automorphism group of K over L1. Okay. So B is incorrect, as L1 over Q. What is L1? L1 is Q adjoined with fourth root of 2. So this is not a Galois extension. We are again using the fundamental theorem of Galois theory. So this is not a Galois extension, as it is not normal. You can check this, that this extension is not normal. You can just work with the irreducible polynomial x to the power 4 minus 2. It has one root in L1, but not all of its roots are in L1, right? Yeah. So what is option C? H1 intersection H2 is a normal subgroup of G. This is true. C is again correct. C is correct, as for all sigma in H1 intersection H2, sigma fixes. So H1 is automorphism group of K over L1 and H2 is automorphism group of K over L2. So sigma, which is in H1 intersection H2, fixes L1 union L2 element wise, right? It fixes L1 union L2 element wise, and hence sigma fixes L1 L2, the composite term of L1 and L2, the smallest subfield of K containing both L1 and L2, that is a subfield of K generated by L1 union L2. This is just K itself, right? Q adjoined with fourth root of 2 and I, so that sigma is equal to the identity map, and hence H1 intersection H2 is just the trivial group, and the trivial group is always a normal subgroup of any supergroup, right? So this is what we used here, and option D therefore is trivially incorrect. Option D is incorrect, as H1 is non-trivial, H2 is non-trivial, but H1 intersection H2 is trivial, right? So that it can't be the case that H1 is contained in H2, right? Because their intersection is trivial. So we don't need H2 is non-trivial here for this argument. Just the fact that H1 is non-trivial will work, okay? So yeah, no, maybe yeah, I might be wrong in this one. Let me figure this out 1 second. So you are looking at the automorphism group of K over L1, right? Yeah, you are looking at the automorphism group of K over L1. So you are looking at all yeah, right, so yeah, I'm correct. So the automorphism group of K over L1, which is H1, I am claiming that this is a non-trivial group, right? Why? Because this, we are again using the fundamental theorem of Galois theory here. So you know that the subgroups of the Galois group are in bijective correspondence with the intermediate subfields, right, of the Galois, of the given Galois extension, okay, right? And what is a bijection from in one direction from subgroups to subfields? The bijection is given by sending any subgroup H onto the fixed field of H in E, and in the opposite direction, the inverse bijection in the opposite direction from subfields to subgroups is given by taking any subfield B and mapping it onto intermediate field B. I mean, in the opposite direction, the bijection is given by taking any intermediate subfield B and mapping it onto the subgroup Galois group of E over B, right? Now assume that H1 is indeed trivial, okay, that is, or the automorphism group of K over L1 is trivial. That means that if you send this group to the corresponding fixed field, which is K power automorphism group of K over L1, which is just L1, right? So which is just L1. So L1 has to be equal to K, right? Because since we have assumed that the automorphism group is trivial, right? So automatically the corresponding subfield has to be the largest subfield of the extension, right? So L1 has to be equal to K, which is a contradiction. So let me maybe I'll just write down the reason behind this. So H1 is non-trivial as L is not equal to K, right? So use fundamental theorem again, or maybe and by the fundamental theorem. Theory. So H1 is not equal to K as L1 is not equal. I mean H1 is not equal to trivial group as L1 is not equal to the entire field. Okay. So D is certainly incorrect. So option A is correct, option B is wrong, option C is correct, option D is wrong. So H1 is non-trivial, but H1 intersection H2 is trivial, right? That means H1 can't be a subgroup. So let us look at the next problem, which is problem 8. So maybe this much space would do here. So we are taking G to be the automorphism group of Q adjoined with the 8th root of 2 and eta over Q, where eta is e to the power 2 pi I by 8. Okay, we need to figure out what is the cardinality of this automorphism group. Okay, so again, as you can see here, so solution, again as usual, Q adjoined with 8th root of 2 comma eta over Q, right, is what kind of an extension? Is a Galois extension. Being the splitting field. I'm sure by now you have figured out how to find out whether extensions are Galois extensions or not. The most useful tool being the fact that the extension should be the splitting field of some separable polynomial over the base field. So as this extension is the splitting field of the separable polynomial Q adjoined with cube root 8th root of 2. We need to mention the polynomial x to the power 8 minus 2 in Qx. Okay. So this is a Galois extension. Thus cardinality of G is equal to the degree of this extension Q. Okay. Now Q adjoined with 8th root of 2 is to Q is 8. The degree of this extension is 8 by Eisenstein's criteria. So what I'm saying here is that you just find out, so this is a simple extension, right? The degree of this extension Fa, the degree of the extension Fa over F is equal to the degree of the minimal polynomial of A over the base field F, right? The minimal polynomial of A over of 8th root of 2 over the base field Q is exactly x to the power 8 minus 2. Firstly, this is a monic polynomial. 8th root of 2 satisfies this polynomial, and finally by Eisenstein's criteria this is irreducible over Q, right? So this is indeed the minimal polynomial, and the degree of this polynomial is 8, so that the degree of the simple extension is 8. So by Eisenstein's criteria you have that this is 8. Now eta is equal to e to the power 2 pi I by 8 as given here, which is equal to 1 plus I by root 2 if I am not wrong, right? Yeah. Thus Q adjoined with 8th root of 2 comma eta is the same as Q adjoined with 8th root of 2 comma I, right? Why? Because eta is clearly contained in Q adjoined with 8th root of 2 comma I, right? And conversely I is also contained in this, right? Because root 2, the point being that root 2 itself is in Q adjoined with 8th root of 2. Okay, so therefore what I'm trying to say here is, thus the degree of Q adjoined with 8th root of 2 comma eta over Q adjoined with 8th root of 2 is just the degree of Q adjoined with 8th root of 2 comma I over Q adjoined with 8th root of 2, which is 2. Thus by the Tower theorem, Q adjoined with the degree of Q adjoined with 8th root of 2 comma eta over Q is equal to 4 times 2, which is 8. Okay, so the coordinate of the Galois group of this extension, that is coordinate of G, so maybe coordinate of G is exactly equal to 8. So 8 is the correct answer. Okay, yeah. Oh no, sorry, not 8, sorry, oops, maybe I did, yeah, this was 8 and this was 2, so this is not 4 times 2, rather 8 times 2, which is 16, right? And therefore the coordinate is 16. Yeah, 8 times 2 is 16. Yeah, so maybe I'll erase this tick mark. So option B is 8 and the correct answer here is 16. Yeah, okay, so let us move on to the next problem. So solution, let G be equal to the automorphism group of Q adjoined with root 2 root 3 over Q. We need to figure out how many proper subgroups does G have. Now here you can use the fundamental theorem of Galois theory, but that would sort of be an overkill here. We can do it very simply. Okay, so Q adjoined with root 2 comma root 3 is the splitting field of a separable polynomial, of the separable polynomial separable polynomial x square minus 2 times x square minus 3 over Q, splitting field over Q. Okay, thus Q adjoined with root 2 comma root 3 over Q is Galois. Further, the degree of this extension over Q is exactly equal to 2 times 2, which is 4, right? Hence the Galois group has coordinate of G, I can say coordinate of the Galois group. Since this is a Galois extension, the coordinate of the Galois group will be equal to the degree of the extension, so is equal to 4. Now any sigma in G permutes or acts on it, so any sigma in G permutes or acts on root 2 comma minus root 2 and permutes root 3 comma minus root 3. Thus for any sigma in capital G, right, sigma maps root 2 sigma maps root 2 onto either root 2 or minus root 2, right? And sigma maps root 3 onto root 3 comma minus root 3. Okay. That is sigma, if you consider root 3 as a singleton set, then sigma is a mapping of this singleton set root 3 into the set root 3 comma minus root 3, so that the image of root 3 can be either minus root 3 or it can be root 3. And similarly the image of root 2, that is root 2, can be mapped onto two possible elements, right? That is, the image of root 2 can be either minus root 2 or it can be root 2, right? There are two possibilities for the image of root 2, and there are two possibilities for the image of root 3. Okay, yeah. Okay, so cardinality of Galois group. Now, thus there are at most 4 possible elements. Okay, maybe we don't need to go there. We can just finish the argument in a few minutes. I mean, in 2 minutes. We don't need to go there. So every sigma in G has order 2. Thus G is isomorphic to Z2 cross Z2, right? Hence G has, how many subgroups does proper subgroups does Z2 cross Z2 have? So Z2 cross Z2 has so trivial, then EA is a subgroup, EB is a subgroup, EC is a subgroup, right? So it has 4 proper subgroups. If you also include non-trivial proper subgroups, then the number of such subgroups is 3. So the answer here will be 4. Okay. Right. So maybe I'll just mention number of non-trivial subgroups. Is number of non-trivial subgroups is 3. Okay. Non-trivial proper subgroups is 3. Yeah. So let us move on to our final question. So we are given an arbitrary prime P, and we are given the finite field of order P to the power n for some n greater than equal to 2. Now we take G to be the automorphism group of K, H to be equal to the automorphism group of K over F. Okay, so by F here I mean FP. Okay, or maybe I'll write it in the same color. K over FP. Yeah. Then we need to say whether this statement is true or false. We need to decide whether this is true or false, that the group G is the same as the group H. Certainly H is a subgroup of G. Indeed, an automorphism of K fixing FP element wise is an automorphism of K by definition, right? So H is contained in G. We need to figure out whether G is exactly equal to H. That is, we need to find out whether, if we take any arbitrary automorphism of K, whether it fixes FP element wise or not. That is what we need to do here. Okay. So the subfield FP of Fp to the power n is given by so you take 0, you take 1, you take 2 times 1, 3 times 1, dot dot up to p to the p minus 1 times 1. Okay, you can check that this is the prime subfield fp of fp power n. This is a subfield, you can check easily, right? And p times 1 is again 0 because the field has characteristic p. Okay, now any sigma in k, I mean in odd k, fixes 1 by definition, or maybe we don't even need definition here. Fixes 1 because it's an automorphism of the field, so fixes 1, and hence it fixes n times 1 for any n in Z. Thus any sigma in odd k fixes fp element wise. Thus sigma belongs to odd k over fp for all sigma in odd k. So the upshot is that the prime subfield is always fixed by any automorphism. Okay, hence capital G is indeed equal to capital H. They have to be equal. Okay, so yeah. So I guess this is it. And so we had 10 questions this particular week, and yeah, so we had 10 questions this particular week, and yeah, we have sort of finished the problems. Chaitra, can you hear me? Yeah, so I just sort of finished discussing all the assignment questions for this week. There were 10 problems. So if you have any question, have you seen the problems first of all? Yeah, so do you have any questions? Then you can ask me. Okay, so you don't have any questions. We still have a lot of time left, but since you say that you don't have any questions, let me think of one other problem that we can solve, and then we can end the session. So can you just quickly tell me what all was covered this particular week in the course? For week 5. Okay. It was only about cyclotomic extensions. I am not aware of this, but okay, maybe. And you guys also have studied Galois extensions the previous week, right? And what was covered in say week 6? I mean this week. Okay. Okay. I mean you are talking about irreducibility of cyclotomic polynomials. Yeah. Okay. So category theory has been. I mean, have they discussed category theory as of yet? I mean, it's completely unrelated. Not yet, yeah. It's completely unrelated to Galois theory, but I'm a sort. I mean, I do category theory. I'm a category theorist. That is why, yeah, I was asking. So I think maybe a bit of basic category theory will be covered. Small amount, categories, functors, and natural transformations. So okay, maybe later that will be done. And do we have any questions as of yet? Let me think. So maybe I'll just speak for about 5 more minutes, and during which you are absolutely sure you don't have any questions, right? Yeah, I also don't have questions right now, but so did you cover ruler compass constructions previously? Okay. Uh, okay. So can you tell me? So this is not. I mean, I'm not asking to intimidate you or anything, but just just since we need to spend some time. So so can you tell me if you take the finite field of order p to the power n, what is the Galois group of this Galois group of the finite field of order p to the power n over fp? Yes, yes, that's true. If that is what fp power n is. So you understand that this polynomial x to the power p to the power n minus x, this is an element in fpx, right? And this has splitting field fp power n. So this, so my question is, what is the Galois group of this extension? I mean, can you find out a concrete group which is isomorphic to this Galois group? Yeah, yeah. Okay, so you already answered the question. I was hoping we'll go stepwise, but yeah, yes, you're right. It's precisely the cyclic group generated by the Frobenius automorphism. Okay, so no point in wasting time. I guess maybe we'll end the session here. By the way, why did you join so late? I mean, did you not know the timing? It's from 6. Okay, okay. Yeah, because a few people joined previously, but they left quite soon. Actually, I understand that there are two TS for this course, right? I mean, one is a junior of mine, uh, and I am the other one. So you guys attend both. I mean, you attended his TA session, right? On Friday. Yeah, and I have to do the same questions, which is why I didn't want to do the same questions, but I was told that every TA has to solve all the assignment problems. So maybe next week I'll be adding a different set of questions, not just from the assignment, so that it would be nicer, more interesting, I would say. Yeah. Okay, so if you don't have any questions, maybe we can stop here because there is apparently no one else in the meeting. So yeah, so we can stop. Yeah.